What does chemical equilibrium mean? From introductory chemistry, you sort of know that the reaction proceeds neither to the left nor the right net. And the extent of the reaction, there's that extent of the reaction, doesn't change. So sorry, this should be dC is equal to 0, where the symbol here, Greek letter C, I think it's C, is the extent of the reaction. We'll get into that in just a second. Also recall from introductory chemistry that the equilibrium, even though the concentrations are not changing with time at equilibrium, so here we are at equilibrium, the concentrations of A and B are not changing. Nonetheless, this reaction is still occurring. Even at equilibrium, A is converted into B and B is converted into A. Just at equilibrium, the rates of the reactions forward and reverse are the same, so you have no net change in A or B, but still remember that A is converted to B and B is converted to A at equilibrium, and that's what's known as dynamic equilibrium. Also, we know at constant temperature and pressure, dG, from a previous lecture, dG equals 0 at equilibrium. That's what we said here. dG is a slope, so dG is equal to 0 at equilibrium. And then we'll get into this in just a second. All right, let's look in more detail what extent of reaction means. Let me define what I mean by extent of reaction, given this symbol C. And this, of course, will be a function of time, because as time goes on, the reaction will be more or less toward the beginning. So let's define this as the number of moles of some reactant species I. So this will be we'll right now identify this with some reactant or product species, but we'll find later on we don't need that I, minus the number of moles of that species at time equals 0, divided by this symbol nu I, where this is the signed stoichiometric. I knew I was a chemist when I could spell stoichiometric, signed stoichiometric coefficient in the balanced chemical reaction. What I mean by signed means negative for reactants and positive for products. So for example, if we have 2A goes to B, say, just make it interesting, 3B. The signed stoichiometric coefficient for A would be minus 2, minus because A is a reactant, and the signed stoichiometric coefficient for B is positive 3. So that's what that means. So note that at C, for some species at time equals 0, this means the number of moles is the number of moles at time equals 0 is 0. So the extended reaction starts at 0, and then eventually when it reaches equilibrium, you'll have a certain number of moles here, and that will be subtracted off from the moles that you started with, and then divided by the signed stoichiometric coefficient, then you get a number which will be in moles. So C is in moles. Let's take an example. Let's take A, say it goes to 2B, and let's make this at equilibrium, might as well. This could be at equilibrium too. And also say at time is equal to 0, we have 2 moles of A and 1 mole of B. So as we said, at time equals 0, the extended reaction will be 0. You're just subtracting 2 minus 2 for A and 1 minus 1 for B. Let's say at time is equal to 1 minute, A now is, let's make it more interesting. Let's make this 1.5, and B now is equal to, you started with 1 mole, but for each mole of A, you now produce 2 moles of B, or if you lost a half a mole of A, you produced 1 mole of B. So the amount of B at time equal 1 minute is what you started with plus what you produced from this reaction, so the total amount is 2 mole. All right, so let's look at the extent of the reaction at time equal 1 minute. All right, so the extent of the reaction for A at time equal 1 minute will be the number of moles of A at 1 minute, which is 1.5 mole, minus the number of moles we started with, which was 2 mole, and we're divided by the signed stoichiometric coefficient. The signed stoichiometric coefficient is minus 1, minus because it's a reactant. A is a reactant. So minus 1. So this comes out to be 0.5, positive 0.5 mole. Now let's look at the extent of the reaction for B at time is equal to 1 minute. That's equal to how much B was present at time equal 1 minute, which was 2 mole, minus the amount we started with, which was 1 mole, and the sign stoichiometric coefficient, A goes to 2B, is just 2. So this is 0.5 mole. In fact, if you just extrapolate this, no matter which reactant or product you choose for an arbitrary chemical reaction, as long as you're dividing by the sign stoichiometric coefficient, you're going to get the same extent of reaction. If you measure A, you measure B, or if you have a more complicated reaction, measure C. No matter what reactant or what product you measure at some particular time, you're going to get the same extent of reaction. So that's why these subscripts here are not needed. So the extent of reaction does not depend on what reactant or product you choose, because of the way it's defined, and that minus sign will take care of disappearance of reactants. So we say in general, we can say C will be defined as the number of moles at some time t minus the number of moles at some time t equals 0 when you're starting it, divided by the sign stoichiometric coefficient. This still will have to be a subscript here because you're measuring a particular reactant, but you'll get the same extent of reactant. So again, the extent of the reaction is measured at some particular time, so that how the extent of the reaction changes as some function of time, which is independent of what you're measuring, that would be how this thing changed. So d n sub I, that species of time, doesn't matter whether it's reactant or product, minus n sub I at time equals 0, as long as you divide by the sign stoichiometric coefficient, which is a constant. N sub I time equals 0 is also a constant, so this is just equal to 1 over nu sub I constant d n sub I of time. Okay, so both of these are time dependent. Or in other words, how the number of moles change at some particular time in the reaction is the sign stoichiometric coefficient times how the extent of the reaction changes. And this no longer has to be, this does not depend on what you measure. So that's kind of handy. We'll find that later on, that the extent of the reaction will be one single number, which will be independent of what we're actually measuring. So that's what we mean by extent of reaction. Now let's look at these two equations and see what we can glean from them. Now, as we said, at equilibrium, dg is equal to 0. So g is not changing. We also said in the previous lecture that dg, constant temperature and pressure, dg will be the sum over all reactants and products of the chemical potential of that particular reactant product times how the number of moles of that reactant product changes. That is equal to 0 at equilibrium. Let's make this handy substitution here. So now we can get rid of the dependence of variable here that's changing with just a single one, so we don't have to worry about C. So this is just equal to the sum of mu sub I, nu sub I, sign coefficient dc. And that is equal to 0 at equilibrium. Now let's consider just a simple chemical reaction, A, in equilibrium with B. Let's write this down, this equation down for those. We'll have the chemical, the stoichiometric sign stoichiometric coefficient here will be minus 1. So this will be minus mu sub I dc. And then, so we did, this is a sum over the reactants and products. We have one reactant, we did that one. Let's do the product B, the sign coefficient is 1, so that's plus 1. I should put here A, mu B times dc, and that's equal to 0. Or in other words, since we have this extent of reaction doesn't depend on A or B, we can say that minus the chemical potential of A plus the chemical potential of B is equal to 0 at equilibrium. Or in other words, at equilibrium, for this A goes to B reaction, the chemical potential of A is equal to the chemical potential of B. So that's an interesting finding. Let's see, is that what we said here? Well, yeah, so we're sort of going here. I'm not quite sure what this means. Equilibrium single component. Well, I guess that just means you just have one component, not A goes to B, but in fact just A. The chemical potential at equilibrium of that one component would be 0. What have we done here? Well, we've advanced our understanding. We've said now that at equilibrium, that A goes to B, the chemical potential of the reactant is equal to the chemical potential of the product. In other words, what you're doing, you're starting out the reaction, the chemical potential reactants or products are not equal, they're out of balance. So the system is going to rearrange so that you're going to have chemical potential balance. So the reactants, the chemical potential of the reactants is going to equal the chemical potential of the products. And we showed that case for a specific case, A goes to B. There's another thing we could sort of extract out of these ideas we just presented. We said that GG is equal to the sum of the sign stoichiometric coefficient. Here we're summing over products and reactants. The sign stoichiometric coefficient of the product or reactant times the chemical potential times dC. Let's see how D changes, how G, the free energy, changes with extended reaction. And this we're going to define as delta G of the reaction. That's the delta G that we learned about in introductory chemistry. That's equal to just the sum of the sign stoichiometric coefficient times the chemical potential of that particular species. C, remember, doesn't depend on whether you measure reactant or product, so we just pull that over there as a constant. And as we said, that's what we have here at equilibrium. So that's equal to 0 at equilibrium. In other words, if we look at G, and now we're actually we know what we're talking about when we put down here extended reaction, we have something like this, reaches a minimum and goes up this way. So right there is at equilibrium, and how G changes with the extended reaction is equal to 0 right there. That the slope of this is 0 right there at the minimum. And furthermore, we said here, we're going to call this delta G of the reaction. So the slope and of course delta G of the reaction will depend upon where you are. If you start right here at equilibrium, delta G of the reaction will be 0. But if you're up here, delta G of the reaction will be greater than down here. The slope of that plot is equal to delta G of the reaction. That's because we're just defining it that way. All right, so keep that in mind.